evening to everybody. My name is Timothy. This night is another day. We want to continue our deep learning training from where we stop. I would like to introduce to you our tutor. That is in person of Salau Mohammed Ayobami. He will be taking us through the deep learning from where we stopped last time. So please let's enjoy him. Over to you, Ayobami.
Okay, sir. Okay, good evening, everyone. So we are going to continue
Good
from where we
good
stopped.
evening.
So we are talking about deep learning. So I want to look at the fundamentals of deep learning. So we are going to continue from where we stopped. So I will be sharing my screen. Okay. So I think my screen has started sharing. Okay. So I think
I cannot hear from you, please.
we can. Okay, can we all
Yes,
see my
yes,
screen?
yes, yes, sir.
Yes,
Okay.
Yes, sir.
we can see it.
Okay, yeah.
Okay.
We can see your screen.
So we are going to continue. So we stopped at this place here. I want to talk about the fundamental concepts of deep learning. So and what we want to talk about now tonight, we are going to talk about artificial neural networks, how artificial neural network operates. So now artificial neural networks, simply called neural networks, and is inspired by the human brains, the neurons in the human brains. So that's where the concept gotten from learn things. So, and one thing there is this is that a artificial neural network always contain at least one artificial neuron. So, and that artificial neuron, it can receive an input signal. After receiving the signal, it processes it, and it then generates an output, which is also a signal. So an artificial neuron takes in an input, generates, it processes it, and generates an output. So now, can several artificial neurons be connected? Yes, they can be. So the connection of several artificial neurons is what we call neural networks. So, and the output where we have neurons connected, artificial neurons connected to one another, the output of a particular neuron, artificial neuron will be the input of another artificial neuron. So here in this case, the output that a neuron A generates is going to be the input of neuron B. So which makes it that they are connected together. So and this they will shape an artificial neural network that is organized in multiple layers. So now the connection of one or more, two or more neurons is what we call artificial neural networks. So that give rise to multiple layers. So now, if we want to look further, we have to understand the concept of what a perceptron is. Now, what is a perceptron? The most straightforward architecture of an artificial neural network is the perceptron. So, and one thing there is that at least one input signal X with a corresponding weight, that is what a perceptron looks like. So, a perceptron actually always have several inputs. And that input can can be X1, X2, X3, and it will actually carry some weight. So where the weights are the importance. So the weight shows the importance or priority of the
We
input
did not
signal.
see. We did not
So
see. Not see what you
a
are.
perceptron can actually takes more than
Our
one
tutor.
Input.
We did not see what you are displaying, what you are saying. Is there any diagram to show that? Or you are still
Yes,
on
there's a
this?
diagram.
Please,
I'm still on this.
okay, 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 all right. Easy.
So now the weight shows the importance or priority of the input signal. So and a perceptron can take in more input signals, and the input signal can we can give it priority due to the weight. So the weight can will show the importance or priority of it. So and one thing there is that also a perceptron in a perceptron we can be calculating the summation of each input signal multiplied by its weight and calculating that which the product between the signal input signal and the weight and the summation the multiplication between and summing it gives us an output with a single number and passing the sum value to a non-linear function which is called activation function. So in a perceptron there is a activation function in it. So that activation function coupled with the summation of the product of the respective input signals with their corresponding weights gives us our final output, which is y and which is ready. So this is what a perceptron looks like. So this is it. What I've been explaining, what I explained in the previous slide, which is this, is just this. So which we have a perceptron, which is a neuron. So it actually has can take in up to n input signals. So saying x1 to xn, and for each corresponding input signal, there's a weight for each corresponding input signal. There are weights for it. So now for each of these weights, now this summation function acts on it. So it sums it up and then the activation function actually the summation is passed into the activation function and then the overall output is the y and the function is given as this. So everything that we're talking about here, this is just it. Where G is the activation function, which is this, and the summation here, this is the product between the respective input signal and their corresponding weight, and the summation function. This is it. Yeah. So sum them up. So and which is just the way which will give us our output, which is y, which is this is the overview of a perceptron. This is what it looks like. So now on to the next slide. So the perceptron itself, um, we are still talking about it, but now, but we need to know how to make the artificial the activation function independent from the input signals. So how can we make the activation function independent? Sometimes the from the input signals actually with the weight and actually meets up with the activation function inside the neuron itself. But if you want to make it independent, we have to add a bias node. And a bias node itself has input signal of one and a, a bias weight, which is WB. So, and we will actually look at what is a bias. A bias is a weighted input signal with the value of one. So the input signal is one, so whereby it is weighted. This is the weight. So it's being passed inside the artificial neuron. And using this and by providing a proper weight, we can shift our uh, activation functions to the left and to the right as well. So that's that about that. So we'll move to the next. Okay. So now looking at this, yeah, this is the perceptron with a bias node. So, and the bias node is independent. So, which you can see here with an input signal of one, as we can see, yeah. So, and it has a weight which is WB, and whereby previously as shown to us, we have our respective um, input signals and weighted weighted functions, which is here. So, and all these inputs multiplied by their various weights is going to be summed all together, and the activation function is going to pass into the activation function, and then it gives us an output. So this is a perceptron with a bias node, and this is the function which is here. So showing us that the product of the independent bias node, which is one, the input signal multiplied by the weighted bias weight, plus the corresponding product of the respective input signal from x1 to xn, which is multiplied by their corresponding weight, and the sum plus the weighted bias, and coupled with the activation function, is what gives us the output, which is y, as seen in this function here. So now, still on the perceptron, now we can mathematically define the output as just this here, where x and w are the vector of inputs and weights respectively. So this x is a vector, which means that it has just the dimension can be from x1 to xn. So, and the same, the weight too can also be like that. So here also having the bias itself, where the bias has an input signal, bias node has an input signal of one. So, and which we are writing it mathematically this way, not specifying the number of input signals and the weights. So this is just a way of not specifying the number of input signals and the corresponding weights.
Hello, sir.
Yes, sir.
Please, that T, that power there, is it the transpose of X or just the
It should be a transpose. It should be a transpose of x. X transpose multiplied by w.
the number of X there?
There's a tensor. Let me
Actually
Yeah, in short, it's
transpose.
just like a dot product because you're multiplying summing the pairwise multiplication is transpose.
You know those input signals have been vectorized. So that T there symbolizes the transpose. But let's continue. It's okay, we can continue. That's not a problem.
Okay, so we will move on to functions. So we want to talk about why we need activation functions. So, and the reason why we need activation function is to provide linearity, non-linearity. So, and there's a reason for that. For example, when we are dealing with linear data, a linear data can be um, separated just this way it is shown in this diagram here, where we have one side of data, just a particular class of data being separated from another class of data. So, and if you look at this here as well, we have a non-linear data where we can't actually differentiate the two groups. So, but there's no way that we can linearize this data the way it is here. So this is just the difference between a linear data and non-linear data. And the reason for activation function is to provide non-linearity. So which we will still see very soon. So now, activation functions, we are still talking about why we need the activation functions. Now, it's to provide non-linearity for using in real-world scenarios. Now, the reason is because if there is linearity in a activation function, the neural network will not be able to learn the way it's supposed to learn. It won't learn the way it's supposed to learn. And the reason is because, we just that we have grouped the data just the way it needs to be grouped. So we have grouped it and the data itself is in a way such a way that we won't allow the neural network uncover some patterns by itself. So now the reason for the non-linearity is to allow the neural network to be able to uncover patterns by itself. So, and also part of it is to define how the weighted sum is transformed into an output. So to access, also to get access to much richer hypothesis space, especially deep ones, is one of the reasons for activation functions. So, and we should know that we need to choose them carefully in our artificial neural networks, and because there are many of them, and technically the same for all nodes in a layer of an artificial neural network. So for every node in a particular layer, so it's they will all use the same activation functions. So, and going to that, we have some popular activation functions. We have the linear, we have the unit step, we have the signum, we have the ReLU, which is called rectified linear activation, we have the hyperbolic tangent, we have sigmoid or logistic, and this sigmoid, we also have Gaussian. Sigmoid and ReLU are very, very popular because they are used often, are used very often, ReLU and sigmoid. So these are the popular activation functions we have. We still have some others, but these ones are the popular ones. And the most often used ones are the ReLU and the sigmoid. So now looking at the sigmoid, yeah, now the sigmoid activation function takes in its input as a real number, and the output, or it gives an output which is between the range of 0 to 1, and which is a larger input. For a larger input, then the value of the output we always get closer or tends to 1. So the larger the input for that comes into the activation function, always gives a number close to 1. So it's just like when we pass in a very large value. So the for the activation function, the value tends to 1, just the way we can see in this plot here. So the higher the value, then the more closer that the output tends to 1. So and the way the signal operates, it's just like a common use. And this is also signal function looks like. It is in TensorFlow, which can be summoned. So, and the way to actually plot this is say B is equals to TensorFlow dot neural network dot sigmoid. We have a comma, then the name. We have sigmoid. So, which is this is a diagrammatic expression of sigmoid activation function, and this is the function itself, the algebraic equation of the function, which is 1 over 1 plus e raised to the power of minus x. So now I want to talk about this here. So we have here as an example of perceptron with sigmoid activation function. Now suppose we have this artificial neuron, and the weights vector are this, where we have the bias, which is 1, yeah. So and we have this here, so which is WT, so which is equals to, that is 5 and minus 3, which is a vector. Yeah. So in this case, is a two-dimensional vector. Yeah. So now the summation function provides us that our output is going to be y, just the way we have seen, which is here, and which is going to be equals to g. G here there specifies that we have the activation function, which is going to be operating on the perceptron itself, the input signal. So this is the bias node, which is 1, which is written here as 1, plus the corresponding um, vector, which is xt here, which is showing this, showing the dimension, yeah, which is from x1 to x2, because the weight has been specified there as 5 and minus 3. Yeah. So the weight for each of the corresponding input signals. So which we have here as 5 and minus 3. So here automatically we know that we have our um, our input signal, which is always tending to xn, but in this case it is x1 and x2. So we have it as 1 plus 5x1 minus 3x2, which is this here. So now using this sigmoid function, I'm going to have this sigmoid function this way here. That we know that we have to find the sum of all between the product of the weighted weight of each corresponding input signal. So which we have,
Hello,
we say 5
hello.
times x1.
Sorry, before you
Hello.
continue, there seems to be a mix-up here. That should be W. I don't know. Stand to be corrected. That should be W because I can see that you have XT, X transpose, then W.
Yeah, that's the way it's being given here. This is the way it is. Just the way it is being given
No, no,
currently.
it's what he wrote there is correct. The x, you see, the x is x1 and x2. So the first term of x multiply the first term of w, and the second term of x multiply the second term of w. That's why
So
you see
this
5x1 and then
exactly
I agree
3x2.
with you.
minus
The
3x2.
expression is correct, but I'm talking about the first one that I wrote WT. And meanwhile, in the
The
formula, it
WT
is W.
now, like I said,
That it
uh,
is a
um,
transpose.
Yes, it's a transpose. It's just when it is 2 by 1, then the transpose becomes 1 by 2
Yes.
matrix. So it's
The
correct.
way the way sorry, the way it's written is correct. Actually, W is a column vector, as in vertical, but the
Okay.
transpose
That's
now
that's
turns it
that's
to
two
horizontal.
by one. Two
Oh,
by. Mm.
okay, so now we want to now look at how to now compute this. So now this is what we want to do. So we actually were looking at this function. So but we are using the sigmoid activation function. So if signal y, which is this, which is the sigma function of 1 plus 5x1 minus 3x2, and we have some particular points. Let's say we have minus 2 and 2. So this is what is going to give us. It's going to give us, we have minus 2, which is going to be just this. We are going to have 1 plus, that's going to be 5. And we have the x1. So our x1 is going to be minus 2. Yeah, so we have minus 2. And we are going to have minus 3 times 2. So which is going to give us 1 minus 10 and minus 6. So which is going to give us minus 15. So now, if this gives us minus 15, and we want to, how did it come about giving us 0.03? Is by substituting um, this value, x, inside the activation function, so which is 1 over 1 plus e raised to the power of, that is minus x, which is going to be minus of 15. So, and computing it, it will give us this output, which is 0 point, that is 0.003. So Now, if we also as well take another point again as 1 and 2, and we substitute it here, so we are going to have our value which is going to be 0 here, because we are going to have 1 plus 6 division function. We're going to have 1 over, that is 1 plus, so we have e raised to the power of minus 0, so which is going to eventually give us 1 over 2, and which is going to give us 0.5, which is written in front of it. That's the output, so which is 0.5. So if we do the same thing for this, we're going to have 0.99. So now, when looking at this, yeah, look at this. Now, if we actually,
Mr. Yoajayi, if you have any question, please ask. Ask.
hello, sir.
Somebody is raising hand. Mr. Yoajayi, please. You want to ask question, please? When we go for that.
Yeah, yeah, I would prefer to ask after at the end of the training.
Okay. All right.
Thank you.
Better, better.
Okay, okay. So I'll continue. So now for the next slide, I have an example of perceptron with the sigmoid activation function. So now, if you look at this, generally we can conclude that now we always have always summation z is less than 0 and output y is less than 0.0.5. So that's for this side, yeah. And we always conclude that always summation is z greater than 0 and output y is greater than 0.0.5. Now, if you go back to the previous slide, yeah. So our output is 0.03, yeah. So, and we have the output, which is y, which is 0.03, and here we have y, which is 0.5, and here we have our output signal, which is 0.99. So now, if you look at normally the way the sigmoid function looks, because it always looks like this. So if you look at it, the smaller, like the rules we gave, said the smaller the the larger the input, the closer it gets to 1. So which is the case here, where we have this input is smaller, so which is corresponding to minus 15, and the smaller the value, then the closer it is to 0. But when we see that the value start getting bigger, you can see that the value tends to 1, which is always between that is 0 and which is 1 here. So this is just it. So we want to talk about neural networks now. So now we want to simplify the diagram. So now let us now look at another formula here where we have this here. We are going to look at this bias node plus the product between corresponding input signals and their corresponding weights, the sum of everything. And we're going to say that all of this itself is going to be called Z. So then G itself is now going to be taking in the answer, or let's say the computed value, and takes it in and pass it in into the activation function, which you have as y is equals to g of z. So now, what if the perceptron provides multiple outputs? So can we connect two perceptron networks to have two different results? So that's a question that what if you have perceptrons that provide multiple outputs, and is it possible to connect two perceptron networks to have different results? So we are going to see that in the next slide. So now, this is it. We can extend it to multi-output perceptron, which is known as MOP. So which means that we can have different neural network, which is ZJ, that is from one, two, three up to J inputs, and as well we can have the output as from one to I. So, but the thing there is this is that when we have different inputs and we have different perceptron, so those different different signals from anywhere that it is coming, and it will compute them and it will give us an output which is y1 and y2 as well. So this itself a neural network where we have different perceptron and input signal coming in from different angles. So takes us to what I call dense layers. So where all inputs are connected to all outputs. So these are all the inputs and they are connected to that. So this output Y1 is actually connected to the input signal X1 and X2 and Xi. And while the output Y2 is also connected to the input signal X1, X2, and Xi. So now, still on neural networks, so let's connect several single nodes which are called perceptron together. So if we have some input layer which is all of this, and we have the hidden layers. Yeah. So and all these hidden layers that we have here are just like nodes. So and where we have different nodes across this way, taking in input signals and also connecting with other nodes that are here. So and then giving us an output layer. So this itself is what I call a neural network. So where different nodes connect together, where different input signals enters into a node, and then inside the hidden layer, which we don't see. So before we now see an output. So this is just the way the brain operates, whereby we have different neurons connected together, which we don't see how they operate. So, and when you want to take a reflex action, for example, if something wants to fall down, or let me say, something bites us on our hand, so there will be this signal, that's the input signal. So it transfers the signal to the brain, where the brain actually takes it in as an input and it connects out to the neurons. And the neurons that is connected to are very, very much and dense. And it computes it and brings out an output whereby to tell you that, okay, I think something just bites me just here. So I have to look at that place and see what is going on there. So that's just the way this looks like. So it's just the way the brain operates. So now to the next one. So looking at what we looked at the other time, we will look at it that the input layers, it takes raw input. And here we have the hidden layers. We don't know what's happening there. So, but that hidden layers, it passes data that needs to be processed. So, and maybe this the data that needs to be processed is going to be given as an input raw input, which is being computed by the hidden layers.
Please, I lost audio signal, please.
So,
Please, can you
but
repeat
we
what you
don't
are saying?
know what is going on in the input layer, which takes in raw Yeah, how the neural network tends to understand and make meaning of what is being passed into it. So, but what we know is that output layer we can use to make a prediction. Actually happens in the network. We don't really get to know because it is hidden. We don't know. Just the way the example I gave just now, that if something bites and someone tends to, like, the signal goes to the brain, then it computes and gives us an output and say, okay, I think this is harmful. Something just beat me just now. So that's just the way this looks like. So now we want to look at a useful note. So now, if there is only one layer in the hidden only one layer in the hidden layer, it is called a single layer neural network. So now, if the number of layers in the hidden layer is more, which is more than 5, so usually it is called, we call it a deep neural network. So for a single one layer, which is in the hidden layer, call it deep dense layers in neural networks, like the image above, with a 3 by 4 or 4 by 4 and 4 by 2 dense layers is there. So here we have 3 by 4. So we have 3 by 4, which means that 3 to 4. We have 4 to 4, and we have 4 to 2 dense layers. So this is a particular dense layer, this one, so which is 3 by 4, and we also have this as well, which is 4 by 4 dense layer, and as well we have this dense layer as well, which is 4 by 2. I hope we get this. I just explained here. So this is 3 by 4, this is 4 by 4, and this is. I want to talk about this here now. So we want to talk about a sample now. Passing. Let's look at passing a driving test. Now let's assume we want to pass both theory and practical tests. So, and where we have X1, yeah, which is equals to topics achieved in theory classes, and we have X2 as hours spent in practical tests. So now we can have the distribution of people who have passed or failed the test before. And the chart is 2D, and as there are two features. So it is either someone passes or fail the test. So that's it, which we have two features. So it's either the person passes or fail, which you can see. Yeah. So now let's go ahead. Now, the question is, will a given node M pass the test? So, though we have or some samples that we have in the original data that we have of people that have failed and people that have passed the test. So now I want to ask that, okay, for a given node M, will a given node M pass the test? So now, if I assume that the node M has an input of 10 and 12, meaning that 10 number of achieved topics and 12 is hours spent training, which are the um, corresponding input signals that we have here as X1 and X2. So now the answer is that we need to train the artificial neural network first. So before we can be able to know if this given node will pass the test. So now we can say training is equals to adjusting the weight. So we need to adjust the weight for each corresponding input signals in order for the neural network to be able to predict for this new node whether it will pass the test or it will not pass the test. And the thing there is that the weight there is that is giving priority. For example, we'll give more priority or more weight to these classes that are here, because they tend to actually be the ones that pass. So, which means that more weight to be given, but a lesser weight to be given to this class. So now what we justify if this node M will pass is the weight that is going to be ascribed to it because it's an input signal already. So, but it's the weight that is now ascribed to it. So, which now this particular one, like I said, is the weight that will justify whether this is. So, just like I said, the solution is to the artificial neural network for the input signals that are first given to train the artificial neural network. So, and lesser weights given to this, so that when we now input this node, then it will be able to tell us that okay, this node, okay, M will pass, or this node M will fail. So now another sample is a classification of objects into predefined classes. Let us see whereby we have inputs of rectangle, circle, and triangle. And the goal is to give a correct classification, whether it is we have a circle, we have a triangle, or we have a square. Now, classification of objects into predefined classes will look like this, where we have the three shapes we want to classify. So, and we have the input layers. Yeah, and we also have the hidden layers, and we have the output layer. So the output layer is whereby we want to be able to predict, okay, classify, okay, this is a circle, this is a square, and this is a triangle. So now when this particular shape now enters into the input layer, so now what it will use is that it uses each pixel is mapped to a single neuron from the input layer. So now, when we say pixel, what is peculiar to deep learning is that for any object or image or anything that is being um, fed into the input layer, it changes them into numerical values. So, and those numerical values are what we call a pixel. So, where we have a pixel 1, pixel 2, up to, let's say, a pixel 900. Let's say that, for example, we have sample that is given is the image is 30 times 30, where we have up to 900 pixels. So it's going to be fed into the input layer, and after that, there's going to be weight. The weight that is going to be ascribed to each of the inputs is this here, which we have 0.2, 0.3, 0.7 that is given. So which is initialization of random weight that takes place in the hidden layers, which we are seeing here. So which have P1, P2, P3, P4 to P900. So all these are being calculated using the perceptron function that we have, that y is equals to, that is the activation function being used. We have the summation from I to n of the corresponding input signals multiplied by the corresponding weight. Calculation that is happening in the hidden layer. So this is a hidden layer. We are considering this. So what's going to be the value that is going to be here is that it's going to say 0.3, because we are considering only this hidden layer here, plus 0.7 times P2, because the input layer that goes into this hidden layer is just P1 and P2. So that's what we have, which is here. So now, if you now look at it here, the impact of the activation function now is going to be added. So we have the impact of the activation function, which is going to be that is in the hidden layer. So which you can say it is B2, whether it is a bias node. Like we said, if we want the activation function to be independent, add a bias node B2 plus 0.3 times P1 plus 0.7 times P2. And we now say that the impact of activation functions nodes with green backgrounds. So these are the active nodes with green backgrounds. That is the impact of the activation functions. So the active nodes with round, where we have B2, B5, and B6, saying that the activation functions has impacted B2, B5, and B6. That's where the activation functions are being used, and thereby we now have what they call the forward pass and the main flow of calculations where each layer takes inputs from the previous layer and processes them, which is summing them together plus the activation function and generates an output and passes them to the next layer is what they call forward pass. So a forward pass is just like we have an input signal from a previous layer and from a layer to another layer to
Hello,
another layer. Yes, sir.
we have less than 5 minutes for this link. So we're going to give out another link after this breakout. You can continue.
Okay, sir. So now the forward pass, like we said, is a main flow of calculations where we have each layer that takes previous inputs from the previous layer and processes them. Like we said, the summation for each weighted input signal, the product, the addition of everything plus the activation function, and generates an output. So the output is then passed into the next layer. So it's just like a dual generating. So it's just like we have this particular, okay, we have these inputs coming, this is a layer. So where we have the input signal multiplied by the weight, and then it's being passed, the same value is being processed and passed to the next layer, and then till it gets to the final output. So that's what forward pass is about. So now let us look at the forward pass in this case here, just what we are looking at before. So, like we said earlier on, we said we have input signal whereby for each pixel. So we have P1 up to P900. Then we have um, B1, B2, B3, B4, B5, B6. So where the ones, the green nodes are the ones where we have the activation functions where they have acted, which is B2, B5, and B6. So we know for this one, which is this. But now the fourth pass here is that the output here is being passed into the next layer. So the output here is 0.2 passed to this. The output here for B1 is 0.6, which is being passed to this. So B3 0.2 is being passed to this particular layer from B3 as well again. So it's passes 0.5 to this neuron here in this layer. So the thing there is that there's going to be a forward pass. As far as there are still layers that are remaining, there will always be a forward pass. So from one layer to another layer to another layer until we have our given output.
Sorry. Can I ask a question, please?
Yes, sir.
Okay, so number one is these values. Maybe I didn't get when you said it. So how did you get them? The ones linking P1 to B2, sorry, the P's, the inputs to the hidden layers. So how do you get those values? And then number two, you said B2, B5, and B6 are where the activation function acted. Then how do you now calculate B1, B3, and B4?
Okay. Like we said, you remember earlier on, I gave an illustration where we don't have activation function actually operating independently. So where we just have the independent, that's just the only the output function, which is why I think which is this. So for emphasis sake,
Okay.
okay, which is just only this. So that's just what is happening here. You
Okay,
got
the
what I'm trying to
sum
say,
then.
sir? Yes, for those ones that are not
Okay.
green. So, but the ones that
Okay.
are green are the ones that have the activation
They be
functions.
acted on. Okay.
Yes, exactly. The independent ones that have the bias node. So that's for that one. So that's why it is that way. And the way to calculate those values, um, for example, the way to calculate those values, we will still get to that actually. So I
Okay.
don't want to go. So these ones are hypothetical values. So they are just hypothetical. So we are just
Okay.
using them to just arrive at to just make the point. No. So now, if you now look at the fourth pass, for the fourth pass to be complete, you can see here we have the output here, which is 0.6, which shows the output which is circle, zero point 0.3, which is square, zero point 0.1, which is triangle. So now for this that is being here, this is just the way the neural network operates, where it takes in input signal, takes in input. After taking in input, and the next thing it does is to now take into the hidden layer where the weights are being acted upon the input signals and carried forward. There's a forward pass from one hidden layer to another hidden layer till it gets to the final output, just like we have here. So now the thing there is this is that we have a wrong prediction here because by default, this is supposed to be that we have a square. So, but we have 0 0.3, 0 0.6, 0 0.1. And in this case here, 0 0.6 here, that's the value that it gives here, which shows that the highest probability is circle with confidence score of 0 0.6. So, but the prediction is actually wrong. So, and why it is it wrong? The way to know is by comparing the results with the actual expected output. So now, for example, now if we want to look at it, after everything we have, so the actual thing there is that by default we know that this is a square. So the actual value that needs to be given to it is 1 to show that okay, it is a square. So now the error there from the actual to this error here is minus 0.6. Here it is 0.7, and from here we have minus 0.1. So now if you look at this value here, now removing minusing these values here and saying 1 minus 0.3, it gives us 0.7. So and this value actually shows that this is the error margin that we have here. So the error that we have, but naturally it's supposed to be a square that we should have here that is supposed to predict for this sample image that is giving us here. So now the way to resolve that is what they call back propagation. Now, what does back propagation that it allows to be able to actually go back in a recursive way. We go back and actually look through into the neural network, whereby because if we look at the way a neural network operates is this is that it's not immediately when you feed it with data, it learns everything automatically. So it just keep unraveling the pattern itself. It learns, it makes error by itself. It happens within the neural network. You get what I'm trying to say? So it keeps going on and it keeps learning, learning till it gets to a particular point where it has been able to predict, okay, exactly what is that thing that is in that, or that is the actual input itself. So that's just the way it works. So now the backward propagation there is the backward pass, and whereby why we need it is because it's to discover the optimal weight for neurons. So when we mean optimal weight, the weight that needs to be given to the particular neuron, whereby it can be able to make the correct prediction. And another thing is to minimize the loss function. So if the loss function is high, that means the prediction will not be high. And the reason is to generate the best possible prediction. And how can we do that? We can use gradient descent algorithm. So which we'll talk about. So now this is just the way backwards moving back. So we'll talk about gradient descent algorithm. Now, what is training a neural network? How can we train neural network? So now in a supervised training process, data is fed to the neural network, and only then the network learns how to adjust the weight based on it. So we already know the correct answers actually, but the neural network itself will keep on adjusting the weight by itself till the actual and correct weight is given to every input signals so that it can make optimal prediction. So now, by comparing the actual and predicted results, we tell the network has correct results and there's no need to change the weight, or it has incorrect result and change the weight and get closer to the correct answer. So, and loss, like we said, is defined as the cost of incurred from incorrect predictions. So there's going to be a cost that's going to be incurred from incorrect prediction, which means that we need to do a backward propagation in order to adjust the weight. And when we adjust the weight, so we can arrive at a more correct result. So now, we're still talking about training a neural network. Now, there's something they call empirical loss, which is empirical risk minimization. The average of all individual losses is known as the empirical loss, and it has to do with comparing the predicted and actual values. Talking about the empirical loss. So for the empirical loss, this is the function to calculate the empirical loss. And we also have the binary cross entropy loss, which is called the log loss for binary classification. And this is where the predicted values are probability rates ranging between 0 and 1. And the final goal is to just solve a binary problem, which is just pass or fail, which has to do with comparing the real and estimated distributions. So, and which this is the function loss. Mean squared error loss models, that is for continuous real numbers outputs. An example of that is what will be is non-binary, so which can be any number between 0 and 100, or which has to do with subtracting the it has to do with subtracting the actual and predicted values. So from there, which is the mean squared uh, error error loss, and finally calculating the average of its squared errors, which is seen here, which is 1 over n of the summation from I to n. We have hxi minus yi all squared. So also, we can use different types of loss functions for different problems. So using these quantified errors, we can train our artificial neural networks to find optimal widths. So can choose anyone, but we have to choose the one that actually suits whether it is binary prediction or non-binary prediction, or that's to do with real numbers. So now, how to deal with loss or error functions? Now, we want to do with loss or error function. Yeah, they are useful as they show how far the actual expected output is from the current predicted output of the artificial neural network. And our goal to minimize the loss function as much as possible, and to bring output as close as possible to the actual value. So this is what we are trying to do, is that we want to reduce the error loss as the time of training increase. As we are training the model, the artificial neural network, then the error loss has to be getting closer to zero as the time increases. So we have loss optimization. Now for loss optimization, the loss to achieve the lowest possible error, which can be the local minima and global minima. You are seeing from here, which this is the local minima, and you have the global as well, which is seen in this diagram here. So now, if W star holds the optimal values of weight vector W, so which is equals to the function, then it gets more complicated when the number of weights increases. So, and how can we do that is by using the gradient descent algorithms. So, in order to optimize loss, we can use the gradient descent algorithm. So, now what is the gradient descent algorithm about? So it is an iterative optimization algorithm that's used for finding a local minimum. So by iteratively moving in the direction of the steepest descent, just like moving forward here, so which is like a step to step downhill in the direction with a negative gradient. And we also have the learning rate. That the size of steps also determines the learning rate. So for a high learning rate, we may miss the optimal point, but but either ways, the main thing there is to minimize the loss actually. So, but for it is better we don't have a high learning rate because it's going to give us more bias. But for a low learning rate, which it will take time, but it will prove effective. So either of the two, it depends on what we are trying to, what we are considering, the type of problem we are considering. Now for gradient descent, um, for here when we have the loss function here and the weight, corresponding weight. So if we have too low learning rates, you can see that this is just the way it's going to be here. So, and which means that the weight is going to be dropping down. It's going to be getting very low, and the loss function is going to actually also be reducing. But for this one, which means that for the low learning rate, we have very very slow, and for this one, which is the just right one, where we have it that the for the weight and the loss, we have it that it is not too low, so we can see it just coming step by step downwards here. And when we have too high learning rate, we can see the way it just goes um, anyhow, just here where we won't be able to optimize the weight just where we want it. So now how do we find a proper learning rate? Is we can use trial and error, we can use adaptive learning rate. So but for the trial and error, it is better to do trial and error actually. So this one is very very advisable to do trial and error. But trial and error will not be advised if the data is very big and it takes time to train the neural network. So whereby for the room for trial and error will not prove effective. So also we can use adaptive learning rate as well. So now for gradient descent algorithm, we can pick any random points in the landscape and compute the gradient using the partial derivative with respect to W for the loss function considering, and take a small step towards the lower stages, which is the steep, just as we are seeing here, and repeat this process until we reach a local minimum. And therefore, we obtain the weight from that point. So just like saying we start from the landscape here, from the top here, step 0 to step n, so till when we reach the local minimum, which is at this point here. So still on the graded descent algorithm. So it is not always that simple because in real world scenarios, the algorithm may stuck. So, but the expectation is that when we are doing it, it comes easy this way. But in reality, we might actually have something like this that we want to now find for reality where we want to find the gradient descent. So, where do we want to start from, or how are we going to do something of this nature? So, and which might actually make us consider some other alternatives. So, but the thing there is that for gradient descent, there's a way to update the weight. And the way to update the weight is just this way, which is the weight itself, Wi of t, is equals to Wi of t minus 1 plus change in Wi of t. So where we have change in Wi of t is the learning rate of delta W. So the way to update it is just using this function, and we will still see all of this when we start in action. So now for this, yeah, the way to update the weight, where we have the error on the y-axis and the weight on the x-axis. So this is just the way to update the weight. Yeah. So we have the more lower and the more we decrease the error, then the better the weight or ascribe to each of the input signals so that we can optimize algorithm. So how do weight changes spread in the network? So now one thing to remember is that the main goal is to decrease the final loss, and recall that we need to use the back propagation algorithm, which we talk about in slide 14. The output here is given to the next neuron here, and the output here is given to the output final output y that is here. So now this is the loss function which is here. So and this itself is being shown here just this way, where we have the way we can decrease the final loss is going to be equal to, that is the output which is given here, and the corresponding node as well, and thereby we have also multiplied by delta A over the gradient descent algorithm, and we are talking about the weight changes spread in the network. We said when the right weights are not ascribed to the input signal, they are going to have issues, and the issues we are going to have is that there is going to be wrong predictions. So using the gradient descent algorithm allows us to change and increases the weight to get an optimal result. So and that's why we have to use the gradient descent algorithm, which is this hypothetical we have input signal x and with one where it's being computed and the output is given to this node and passed on to y as the output here. So which is mathematically shown here this way. And here, this way we can calculate all the weight from output to input. So the good news is that we do not need to do this practically in our application because propagation is implemented in different deep learning frameworks. So it is just there. So it's just there in the code. As you initiate it, it does that inside while it is training the neural network. So now for the adaptive learning rate, in contrast with fixed learning rate, the value of learning rate may vary over time, which means that it may become larger or smaller. And factors affecting the value of the learning rate can be the learning speed, which is for the algorithm that is being chosen, or the size of weights and the value of the gradient. Also the optimization algorithms also as well also affect. We have the Adam, we have the Ada Delta, and so on and so forth. But the one that is being used most of the time is the Adam algorithm that's being used for optimization in the neural network. So the Adam algorithms. So we're going to talk about use cases of artificial neural network, and use cases are, for example, a Google Online Translation tool. For example, Google Online Translation tool is if you want to read a language that is not in your dialect, and Google can translate it. Google has where you scan and it translates it. Maybe it is Hausa that is written on a wall, and you just snap it, then it's going to translate it back into English for you. So, and another one is the stock market prediction. You can use deep learning to do forex trading and so on and so forth like that. So, for stock market prediction, and as well, we can use it for face recognition, and we can as well. So, whereby we can estimate age of people based on the data we have used to train the neural network, and also for image completion. So, where an image is not complete, then we can use it to complete an image, and this is being used by agencies like FBI, CIA, Interpol, and stuff like that. So, can use the image completion an image if they don't know. So to scan through all data, they have a lot of faces, and it's going to complete the faces. So those are use cases, and we have suggested projects and general ideas. We have for beginner levels, we can go with image classification to identify the class of a given image. And still at beginner level, we can say visual tracking, locate moving objects for surveillance. And as well, we have face detection for beginners, which is very, very popular when it comes to when you start learning deep learning. So we have face detection, and also which means to track and visualize human faces. And we have for intermediate image caption generation to analyze the context of an image to make a caption. So for all this that is here, there are use cases of artificial neural networks. So, but what will make them very, very like accurate is the amount of data that we are going to use to train the neural network. So another one is text to image. That's for intermediate, to generate images from given text, and also gender or age detection, estimate human age using facial features. And at expert level, we have human face generation, to generate unseen human faces, and also colorize black and white images, make black and white images colorful using a deep model. So these are suggested project ideas. So still under suggested projects, we have Intelligent Transportation Systems Lab, where we have autonomous vehicle, where vehicles can drive themselves. So vehicle detection and tracking as well. We have vehicle type classification, vehicle pose estimation. We have for drivers, we have face pose detection, driver actions detection, and driver drowsiness detection. So we can have deep learning actually have a lot of use cases when it comes to transportation. So those that are actually into the field of transportation policies, transportation engineering, can find this very useful. Deep learning very useful. So now we're going to have an assignment, and the assignment that's given to us is this: we're going to find our field of interest, and there we are going to do four things. Choose a field of interest, what you want to solve, or a deep learning project that you feel like you want to do, and find the issues that can be resolved using deep learning for that field of interest you chose. Find an issue in that area and collect some academic publications about it, and share your titles to discuss. So now for this one year, this assignment is what will allow us to be paired for our final project. I'm going to do a final project where we are going to be paired together, because I won't pair individuals. I don't want individuals to do this, so that we can work hand in hand together. So individuals have to work together. So at least when we are going to submit this assignment to um, the official website for Team Our Programming Consult, where we can access it. So we'll be able to group people into the groups, because at least some people will choose some area of interest that are almost the same, which that is likely to happen. So we are going to group people into groups of 2 or 3, depending on the population, or group of 4. so we can have the projects, the topics or field of interest we have chosen, so we can work on it for the final project. So we can not only to work on it. The reason to work on it is, like I said from the beginning, is to be able to share the code and write a paper on it. So that's the reason for that. So in the next class, which is tomorrow, I'll call on. Okay, maybe let me give it to you next week Monday. I'm going to bring this issue up. It's about choosing a field of interest, and so we have till Monday to submit to the official website or this email that is here. So, and where we'll go through it and group. From there, we'll use it for the grouping. So that's what we're going to do about that, because we have to publish a paper in this area. So the group will publish a paper or have a write up where you can publish or we want to publish. So I know we are researchers and want to publish something on deep learning. So these are some references where we can go and check some things out on deep learning. You can go to this website here. So see some useful things here about deep learning. And so if there's any questions, some questions are welcomed. So before we end the class.
Thank you, sir.
Yes, sir.
Yes, sir. Please, first of all, I would like you to just go back to um, the slide before this one, sir, where you have some references
References.
that those websites you want us to, or those. Yes, sir.
Okay.
Thank you, sir.
You will be given this slide. So
Thank you, sir. I just tried to just screenshot it so I can
okay.
work on it.
Other questions, please. Audience questions, please.
Hello, sir.
Hello, sir.
My question is all these mathematical equation we are displaying, is it input in the Python or will be the one input it in the Python?
You are not imputing anything in the Python. Everything comes readily with the framework, with the architecture itself. So you don't need to do it. So we
Okay.
are just showing it for practical sake
Okay.
and for theoretical knowledge. So that's just it.
Okay. So that means that any result we're going to get from the computing aspect, if we can do it manually and we're going to have the same result.
The one thing about deep learning is that you can't do it manually. There's no manual this thing there. Because if we were to be able to do it manually, we won't be needing deep learning. But the point there is that we are showing all these things for for us to understand that these things have a mathematics behind it. It has a
Okay.
concept behind it. So it's not just that it just happens just that way. And because we will still go into writing codes, we will write codes. So by the time some people would like us to see the connection between the theoretical concept, the maths behind it, and also the coding as well.
Okay.
So that's what people would love to see. So which we will still do. We are still going to write codes, but this is just the foundation, just theoretical concepts. That's just all. We just want to see how it works. That's just it.
Let me come in.
Thank you.
Let me come in here.
Hello,
Doctor,
sir.
Yes, sir.
let me give you a very good instance. When you were in the university as an undergraduate, you were doing something on matrices that time, if I'm not mistaken.
Yes.
You do matrices
Yes.
of matrix multiplication, where you have 2 by 2 matrix. Later, you have 3 by 3 matrix. Hope you are getting me, sir.
Yes, sir.
Now, later you have 4 by 4 matrix. Now it becomes more difficult to do them manually. Am I correct?
Yes, sir.
When you have matrix of 10 by 10, if you start doing it manually, to multiply together, go and
That cannot be
calculate
done.
almost a week, you are still on it. And eventually you will still make mistake.
Sure.
Yes, yes.
the chances of making mistake is very high.
Very
That
high,
is exactly
yes.
what is when we started this protocols. If you remember, when we started the deep learning, we said deep learning involve millions of data. So you want to handle 1 million data
Yeah, manually.
by hand, by
Mm.
which calculator will do that for you? Let's proceed.
That
Let's proceed, please. Other question.
is very good. Mm.
So only what you need is the scope, the framework, how it works.
Okay.
So that by the time we get to the practical, when you're talking about artificial function, artificial this, artificial that, it will not be strange to you abstractly.
Mm.
So that is why this theory is very essential.
Mm.
Once you have the code, once you know the code, you can adjust the code yourself for life. It has become yours.
Mm.
And you can think of how you can manipulate yourself to use the code to write papers. If you are in the field
Thank you,
of
sir.
if you are in the field of stat analysis, economics,
Mm.
computer science, any field you are, once you if you are in the field of agricultural extension or agri science or biology, once you mention that you want to introduce machine learning or deep learning or data science, no supervisor, no lecturer will reject it for you. They would like to welcome it because that's
Mm.
the latest in the town.
Right in the area, yes, sir.
They would like to welcome anything artificial intelligence, anything artificial neural network, anything
Mm.
ANN. They welcome it. That bring it into this course, to this discipline. Let's see how it will work. So that's how it is. Dr. Ayo
Thank you, sir.
Ajayi, can you please ask a
Hello,
question?
sir. Thank you, sir. Good evening, good evening, everyone.
You're welcome.
Good evening, sir.
Yeah, I'm a biologist, and going through the slides, I could see that a lot of mathematics is there. So my question is for somebody from a non-mathematical background: will he or she be able to cope with the rigors, with the mathematical rigors of deep learning when the practical starts? Because
Okay.
when I went through the slides, I couldn't figure out much because my background is not really mathematical. So can somebody who is not in the mathematical science fields or specializations cope very well with deep learning in any application? So that's my question.
Okay. Okay, sir. That's a very good question, sir. And the answer is yes, you will cope, sir. Because, in short, deep learning has more applications in the medical field than any other field for prediction of cancer or cancerous cells or trying to the brain detection of brain tumors. For example, let me give you a use case, sir. So now we know sometimes in some general hospitals, if you want to check the results for an MRI scan or any type of scan that where the specialists they are not much in that general hospital, maybe there are always one or two, or maybe three, and maybe they are on leave or they are not on seat, and it is urgent to analyze that scan. So how can we analyze the scan? And while those people are not on seat, and they call them, they say no, that they are not on seat, that they should wait for 1 week, that they are in another state, that they are working. How can we do that? Now, this is the way to do that. I'm coming in, so I will answer your question with the way I'm approaching it. So we can say that okay, since the inception of that general hospital, there must have been an archive where we have different brain scans or stomach scans or X-rays or X-rays that has to do with fractures and a lot of things. So if we can have access to all those scans and take it and turn them into a data set and train them using a deep learning model, then when there is no specialist on seat, all we just need to do is take the scan from the new patient, pass it inside the model, and the model will be able to tell us this person has a fracture, or this person has internal bleeding, or this person has a brain tumor, which is malignant or not, so or benign. or anyone it is. So it has a lot of use cases whereby we can detect, okay, if an eye has cataract or not, depending on scan or whatever, or image, or any type of image. So that's just the way it is. So all the era has come whereby we don't really need to rely and stress people. So all we just need to do is get a considerable amount of data and then train it, and then we get to benefit from it. Especially in the health sector, deep learning is very, very, very helpful. Very helpful. So I hope I'll be able to answer your question a little bit, sir.
Please, I still need for that clarification. What I'm saying is that with all the mathematics involved,
Yeah, you
can
don't need
I?
mathematics, sir. You don't need
Okay, okay,
mathematics. You don't need it. You
okay,
don't
all
need it,
right.
sir.
That's why I'm
Dr.
going passive,
Ajayi,
sir.
the mathematics we did is just for you to know how how that thing is related, how they are
All
connected.
right,
If you want to do your work, but then we're writing the code, you don't need to write any mathematics at all.
You know, right, mass. Yes,
Only
you're not
what you need
right
to write is
anymore.
your code. Once you write the code and you search your data set, you write the code and you run it and give the result.
all right,
Nobody will be asking you
okay,
how you get that result. Only they want to see
okay,
them is the code. Inside the
And
code,
all right,
moreover,
all those equations are already in the back end. They have been written in that code.
okay,
They are in the back end.
exactly.
all right. Thank you,
Okay.
Okay, sir.
thank you, sir.
Ayobami, is that moreover?
Yeah, moreover, the thing there is this is that when we are writing a paper, so there might be need to specify the mathematical equations, and that is available on the net, or and where you can see in other publications where you can
All right,
actually. So that's just it. So you don't need
okay,
the mathematics.
thank you.
Ambassador Kazim Olajide Makinde, over to
Yes,
you.
sir. Thank you very much, sir. Good evening, everybody, once again. Good evening, our facilitator and
Really,
Team
sir.
R. Um, I'm very, very happy for this training in the sense that I'm in the field of accounting, and I am planning towards engaging a PhD program. And I've been planning on how to use deep learning for that PhD thesis. But the challenge I'm having, or probably where I'm getting confusion, is the aspect of these three key aspects: AI, machine learning, and deep learning. So I don't really know the the relationship or the difference between these three aspects when it comes to accounting related field, because I want to believe that the essence of this training is to solve a business related problem, economy related problem. Let us leave the side of whether writing articles or writing whatever. We should be able to use this the aspect of this deep learning to solve real world problem. So if the facilitator can just give me a kind of relationship or the difference, or how they are related when it comes to solving real world problem. For instance, in financial modeling, in predicting or forecasting a business world situation. So that is just my own question, sir.
All right. Okay. Okay.
Hello,
Okay, sir.
sir.
Yes, sir. To answer your question, sir. So deep learning, what I don't know in your field or the field you are considering and what you want to solve, is there data? That's the first question. Is there access to data?
Definitely, definitely,
So
there's financial data.
okay, good. So if there is data and there is something to predict, then it will work.
Okay.
Because recently, okay, I used autoencoder neural network on a particular data. So and the data has 7,000 up to like I think 12 or 13 columns. So I use it to build the deep learning model. So and I have a target variable, and I have features. So it was the features I trained, and I was able to get the model that I want. So as far as, and that's in area of blockchain. So, but as far as there is data, and that we know that okay, we have data, then we can use deep learning. So, and the data must not be small data; it has to be very large data, not a small data, so we can actually have something that is very efficient. So, and we can also deploy the solution as, let us say, for example, in financial this thing, maybe we just basically deep learning
Like
solutions
financial
are
modeling.
always, yes, the deep learning solutions are always actually being deployed for usage, maybe for companies to use, or for businesses, small businesses, SMEs to use, or anything. I don't know what you're trying to consider, but if I don't know if you have drafted the proposal of your thesis, or I don't know, but however it is, if there is data and we see the research questions and the objectives, then we can know how it will go. So that's just it, sir.
Then the aspect of the relationship between those three key elements, machine learning, deep learning, AI, and what's how are they related, or
It
they
depends on if you want to. The thing there is, if you want to actually provide a solution, like for example, now when we say AI, now AI, artificial intelligence, is just creating a human-like or something that mimics a system that mimics human behavior, something that thinks like an human. So if something you want to do relates to such thing, that's when you need the use of AI. Now, if it is machine learning, where you just want to build a model, a ML model, whereby for prediction, that's when you need that. So, but when you now need deep learning, is when you need also to build a model and you have a lot of data. That's when you use deep learning. But everything is still classified as AI. When it is called AI is when we want to deploy it for the world to
okay.
use it, like whereby two or more or three people can use it. So when it's not that I just only build it for my own self. So, but it's still, as far as I know, deep learning (ML) is still in the domain of artificial intelligence. So that's just it. So it now depends on your research work that now let us know which area we are going to bend to, whether we will actually use machine learning, AI, or deep learning. So anyhow it is, maybe they intersect or not. So it depends on your research questions, sir, and objective.
Okay, thank you, sir.
Okay, sir.
Hello, Bravo.
Is there any other question?
Yes. Hello. Hello.
Hello, ma.
Yes, sir. Please, my question is actually on such example that you gave now, like getting the maybe MIR or something that you called it, like having physical data
Yes,
that
ma.
you need to put together and convert it to the soft copy of such data that you need for your as your data set. The
Yes,
process
ma.
of taking it from that level of hard copy to taking it to the level that you'll be able to use it to run your data as your data set. How do we go about we are trying to help us share us into groups whereby we say the particular areas we want. How do we get this data converted to a level, process it to a level that it will be useful for us for whatsoever we want. The process it
Okay.
goes through, how to clean it, how to do all the things that are involved.
Okay. To answer that question is very easy and simple. For example, now when it comes to deep learning models, and that has to do with image, yeah, when that has to do with image, we need a good camera. So although if we might have all those scans on ground, so we can't just use anyhow camera, and because the reason is because we have to do data augmentation, we have to do data normalization, whereby we are going to extract features from those scans. Features like this, we have to add the true labels and the false labels, where we are going to differentiate between which one is a tumor and which one is a clean scan that is not a tumor. So first of all, we gather as much as possible scans that we can lay our hands on, which is the hard copy, which is the one that comes out from the let's say from the lab where we get the scans from, and there might be a database or an archive in the general hospital or the hospital where it's being kept. We get all of them. We take the liberty to get a good camera. I'm not saying phone camera. I'm not saying phone camera. I mean good camera. Like all this Canon camera or anything that is high level grade camera, we snap them and we have to make sure that the pixel size is very big enough so that we can be able to extract features that is needed from the images. So when we scan all the images, after snapping rather, or if it is to scan the images to scan, can scan depending on how we want to do it. So we snap all the images, we now turn them, we take them into our system. Yes, so then we now give labels to it. This one is we can say tumor one, tumor two, tumor three, which means that's tumor. N1, not a tumor, N1, N2, up to maybe 10,000 scans that are not tumors, and let's say 10,000 scans that are tumors, or depending on how plenty it is. So when we now get that, we will now be able to like say, okay, this is a tumor, this is not a tumor. Then when we tell our neural network that and feed the data in, it will learn it by itself. That okay, this is a tumor, this is not a tumor, this is a tumor. It can take it days to learn it depending on the number of data that we have. So the longer, that's why we're talking about learning rate. So we have to make sure the learning rate is low so it will learn by itself, uncover the the pattern and learn which one is a tumor and which one is not. It keeps feeding itself over and over again, doing audio backup propagation, feed forward, forward pass, everything. So it does everything itself, depending on the architecture we choose, whether it is autoencoder, whether it's convolutional neural network or recurrent neural network. So after that, then when we will now bring in different scan that is different from the one we used to train the neural network, we'll bring something new that is a tumor. So we'll now introduce it into the model, and it will now be able to predict correctly that, oh, this is a tumor. So with that alone, we can deploy it on a system or on a laptop in the hospital premises, whereby we don't need an expert to actually analyze. We just take the scan, we scan it, that scanned a scan, we take it, pass it inside the model, we input it, then all it just does is predict it. This is a scan. This scan is for this patient has maybe, let us say, level 2 or grade 2 tumor, or this thing, maybe it is benign or malignant. Then this person needs medical expert attention or needs a surgery, depending on how we want to do it, and for the neural network to be able to tell us whether the person needs a prompt, maybe he needs radiotherapy, whereby they use all these things to kill all these tumor in the person's brain, or maybe anywhere, anything that has to do with it. So that's just the way it is. So, but that's why I said that the main thing is this: is we want to teach us the basic foundation. After that, we teach us how to um, use the code, how to build a neural network by looking at different cases, and as well, we are now going to choose an area in our respective fields. We are going to use deep learning to solve a problem there, and you can go ahead after solving it. You can go ahead and you want to publish the work, no problem. We don't want to publish, no problem, but we'll see it that we push you to the level you will publish. So that's just it.
All right, thank you.
I hope I've been able to answer your question now.
All right, thank you. Thank you.
Yes.
Another question? Other question, please. We're having less than 10 minutes. Other question, please. Okay. No other questions.
So, sorry, sir. Please, sir.
Okay.
Such situations, do we have a databases that we can get such pictures apart from getting it from the hospital? For such cases, we don't want their data.
Yes, ma'am. Yes, we have a lot of databases. Very plenty.
Okay, we can
Very,
use
very
that
plenty.
instead of the one of the hospital.
Yes, we can use that, but there might be variations. So, and the variations, well, for example, from the things I've been saying, the plenty the data, then the voluminous the data, then the better. So that's just the point there. So we can use any other sources. So that's not a problem.
The law of central limit theorem has to come in that area. So the more voluminous data is, the more correct your results will be. So that does it. Deep learning is all about millions of data, not just 100, 700, 500, 300. No, at least starting from maybe like 5,000, 10,000, 20,000,
Exactly.
10,000, 1 million. Yes, good. So that does it. That does it. So other questions, please, audience. Okay. If there's no question, I'd like to appreciate the partner tutor tonight. Thank you very much. We thank you and on behalf of the Timar Programming Consult. So we appreciate your effort this night. Thank you very much. So good night, everybody.
Okay,
Good night,
good night.
sir. Good night, everybody.
Good night. Good night.